Eyeglass, Amatic manufactures eyeglasses for different retailers. They test to see how many defective lenses they made in the time period of January to March. Okay, so here's all the different defects, and that seems like a lot. Well, all right, so do the data support the notion that each type of defect occurs in the same proportion? So in other words, are these different types of defects equally likely to occur? If they were, then all of these should have been roughly equally distributed, right? So there's 13 different defects here, different types of defects. So 1/13. So therefore 7.7% of them should have been scratches. 7.7% of them should have been spots and bubbles. Okay, so that, I think at a glance we can see that that does not appear to be true, right? It looks like we're way more likely to get a scratch than we are to get a spot and a bubble. So I think on the surface this is obviously going to be rejecting the null, but let's go ahead and run the numbers. So this is again a goodness of fit test. So we're going to go stat, edit, enter in all the data into list one. I need all of these to be 13%, or not 13%, but 1/13 likely, right? So I need my probabilities here to all be 1/13. So I'm going to cheat a little bit here. I'm going to go list one raised to the 0 power. So that'll just make all of these ones times 1/13. And we're going to store that right here in list two. So notice that just turned all of this. So it took all of these here, turned them into a 1, and multiplied it by 1/13 to give me this frequency list. So there's my observed values. Here's my frequencies. So then for list 3, we're going to make these the expected counts. So I'm going to go list 2 times, we need to add all those up. So let's quit out of here. How many different types of defects are there? So I'm going to go list, math, sum, list 1. So there's a total of 25,891 defects. So now I'm going to go stat, edit, and I'm going to go 25,891 times list 2. So it's going to take all of these and multiply it. So there's my expected number of defects. And now we're going to do the formula observed, so that's list 1, minus expected, which is list 3, squared, divided by list 3. And so there's my chi-square values. Did that actually work? Those seem awfully big. Let's try that again. List 1 minus list 3 squared divided by list 3. Oh, there they are. Okay. Some of those are gigantic. So then we're going to go list, math, sum. We're going to sum up, what was that in list 4? Turns out to be a huge number. I don't even need to run the chi-square test on that because that's obviously going to be 0. But that is so big, I'm worried I made a mistake. So I'm going to go stat, test, chi-square test for goodness of fit. My observed is list 1. My expected is in list 3. Degrees of freedom is 12. And calculate. There's that chi-square number. Probability 0. There's all the contributing factors. Remember how big those numbers were? There they are. So I didn't make any mistakes. Remember, if your calculator will do the goodness of fit test, it's not a bad idea to just go ahead and run it that way. But I had to do it by hand because some of yours won't. So let's see. The null hypothesis would be that the defects are equally likely. The alternative would be the defects are not equally likely. Now you could say that a bunch of different ways. You could say the probability of any of the defects are all equivalent. A bunch of different ways to say that. So what is it? Our chi-square number is gigantic. Chi-square is equal to 13,476. The probability that our chi-square with 12 degrees of freedom is as big as 13,476 is 0. So we reject the null. We have strong evidence the defects are not equally likely.